Yeah, just started. We can start.
Yeah. Okay. So all of you people who have joined, you have begun preparing for placements, is it? So VLSI related job placements. Am I right?
Sure.
Yeah, got it. So yeah, I mean, actually, so although this class is related to embedded systems, uh, at the end of the day, any device which has a chip inside it, which has a processor inside it, it cannot work without the work done by an embedded systems guy. Okay, although you need a designer who designs the chip beneath, but on top of it, there runs a firmware. Only then a chip is, worthy to use to any user. So in this session, we'll understand what are all the aspects involved throughout embedded systems journey. So whether you are beginning to learn it, whether you need to find use cases for any embedded systems that you are bringing up, right? All those we'll discuss in here. And also we'll discuss the motive as to why embedded systems have a good knowledge on embedded systems is also needed to understand system any systems working right in a good manner. So it's not just the chip beneath, it's also the firmware which is present above the chip, right? So here you can see this see my screen. So this is actually a document which I've taken from online, right? I'm using the same document, but I wanted to teach you. I wanted to give you exposure to this document, right? So see, there are all arrows going from this embedded systems thing in the middle, right? There are arrows, many arrows going outward. The first arrow that you can see here is what is an embedded system. It mainly an embedded system is comprised of any electronic device, electronic system that incorporates a microprocessor within their implementations, right? So mainly if you talk about any embedded system that you have, it has at least a tiny microprocessor within it. You have all learned about 8086 microprocessor. Anyone, can you please respond? Have you learned about 8086 microprocessor? Have you learned about 8051 microcontroller in your BE? Guys, please respond, anyone. Yes, no, yeah. So you have studied, okay, you're currently learning 8051. That means you're in your third year of BE, is it? Vikas, Kishan, Hari? Okay, great. So 8051, it's a microcontroller. That's okay, you're in fourth sem, got it. So that's exactly that's exactly the heart of an embedded system, right? So a microcontroller is a heart of the embedded system. So you can just remember embedded system as a system that has microprocessor within it, right? So why do we need a microprocessor within an embedded system? I mean, why is it a heart of the embedded system? It's because it simplifies system design. Let's say you are designing a traffic light controller. Okay, you are designing a traffic light controller, or you are set out on a machine to design some system. Firstly, for controlling the traffic, so you're designing a traffic light controller. So you might think this is very easy, right? You can simply design a state machine, a finite state machine, which switches the traffic lights based on timer that you give or based on some inputs that you give, right? So we can design an hardware, just an FSM, and build a chip out of it. Why do we need a processor for this aspect, right? Of course, that is a first thing that you can come up with, and that's the easiest thing, and that's the low cost thing, right? Lowest cost, just a direct hardware that you are building and designing a chip out of it for that purpose. But let's say tomorrow, the same hardware you want to use for controlling something else, right? You need to again design one other hardware for it, one other state machine, entirely different state machine for that purpose, right? That means for every purpose that you are trying to solve, you are trying to build a different hardware. So that's the limitation of the approach that you take, uh, in which you want to solve a problem directly by designing a dedicated hardware circuit for it, right? So instead of that, what people have done is they build a single microprocessor, just like 8051, and based on the use case that you have, you just write a program, you just write some assembly or C program, such that your use case will be solved easily using the same microprocessor, right? And one biggest advantage, if you talk about the cost aspect of this is, let's say you have to get these chips manufactured, right? Let's say you are designing a traffic light controller. You have to get this chip which you have designed, this FSM which you have designed, you have to get this manufactured by a foundry, any foundry, right? So for traffic light controller, you're giving this design, this traffic light controller design to the foundry. Later on, you want to solve some other problem, then you need to come up with a different hardware design totally, right? That you'll again give it to the foundry. So it is cost wise, if you look at it, when you have different hardwares, you cannot mass produce it easily, right? So your cost would be higher. Let's say you want to manufacture 100 traffic light controller chips. You only have the requirement of manufacturing 100 traffic light controllers. So in that case, let's say your the reticle that you have. So within the foundry, they build these designs on reticles, right? So a reticle can accommodate, let's say, around 1,000 chips, but you only require 100 chips. And at a time, you can only manufacture only single reticle with all the chips on it are the same design. That means out of 1,000 chips, you're only able to utilize 100 chips for your purpose, right? So that's why purely hardware approach might not scale in all the cases. So instead of this, what you can do is you just submit a microprocessor design to the foundry. So you manufacture in many microprocessors, right? Same 8051 8086 microprocessors, let's say, same microprocessors on scale, and you can use each of these microprocessors for different purpose, for different use cases, right? So here it says, so that's one advantage. And second advantage is we can easily make modification and scale our design, entire system design. So there, these are all the arrows going towards other sections, but there is one arrow here which is coming towards embedded system. Let's begin with that. Right. So here you see. Let's begin with this. So we all know that nature as a whole is represented. I mean, as far as electronics is concerned, it's represented with voltages and currents. Right. Let's reach to embedded systems from these laws of nature. You have all gone through this laws of nature in your BE degree, right? Ohm's law, all these Maxwell's equations, right? So these are the laws of nature. These are the laws on which our nature is working upon. Now we are abstracting these laws of nature into circuit elements, right? These are inductors, resistors, capacitors, sources, voltage sources, independent, dependent sources, right? All of this. Now using these, we are forming amplifiers, right? Transistors and amplifiers that you have learned. Now, once you have learned this, you can actually either switch to analog domain or digital domain. But as you all know, microprocessor means digital mostly, right? So it is all about digital circuitry. So if you want to go into analog domain, this all comes into the picture: analog systems, right? Control systems and all. But let's focus on the digital systems, because we are focused on embedded systems, which are digital. So all these amplifiers, you can have digital abstractions for all of this. That means logic gates, right? So these logic gates, you use them to design some combinational circuit, some complex combinational circuit, let's say multiplier, right? An adder, right? You can build an adder using many logic gates. Now, once those adders are done, that's just a combinational logic. But all of us know that a processor works on a clock, right? So basically, if you look at it, a processor at the end of the day is a complex state machine, wherein it is executing instructions clock by clock as a state machine. Okay, so if you take combinational logic and attach clock to it, attach state machines to it, that becomes a processor. So you have both combinational logic. Let's take an example of ALU, and also you have a state machine running within the processor. That's a sequential circuit, right? So that's a clocked abstraction for your digital circuits. Now, it's not just about digital circuits that we learn. In order to program a device, just like how we are programming our 8051 microcontroller, we should build an entire ecosystem around it. We should build an ecosystem around our hardware such that software guys can write their code. How? You have hardware below and you have software above, right? You want to bridge this gap. you want to control your microcontroller by writing programs. So whenever a hardware guy designs a processor, how does a software guy know how to program it? The hardware guy designs corresponding instruction set architecture for that hardware, right? So for example, 8051 that you have learned. So within the 8051 microcontroller, there is a processor, CPU. That CPU, the atomic operations that are performed by this CPU are called as instructions. So any processor, the language that it understands is its instruction set, right? For example, you have separate instruction for add, you have a separate instruction for mul. If you pass this add instruction to the instruction pointer register within the processor, it will perform addition. The ALU will perform addition. Similarly, if you pass this multiplication instruction to the instruction pointer register, our processor will perform multiplication. And these are the operands that we are giving to the instruction. These are the set of registers, right? Your operands are stored in the registers. So that's what instruction set architecture talks about. Take your digital hardware. Now you give a provision to the software guy to tell him how to operate this hardware. Pass these set of instructions so that your program can be run on this hardware, right? So every processor, let's say right now these days, ARM processors are in demand. RISC-V processors are in demand. Every processor that a company designs, they also give instructions architecture document for that processor. Okay, so that's how we have begun. You have started to build a system around a hardware. Now, right, so instruction set architecture, it gives us a set of instruction which is mostly written as assembly language code, right? So add, mul, these are part of assembly language, right? Now, but we don't want to program devices using assembly language, right? It's very cumbersome. You need to know the registers, right? You cannot directly use the registers. I mean, it's very difficult to write a program in this manner, use the instructions of the processor and also use operands as actual registers present in the hardware. So that would be difficult. So what they have done is anyone can tell this answer. So on top of this instruction set architecture, what can sit on top of this instruction set architecture such that we can easily program the hardware? We program the hardware using C, right? Anyone has done it? So 8051, whoever has responded that they are studying 8051, you have written programs in C, have you? Please respond, anyone? Yeah, so you have written program in C. Have you written a program in assembly language as well, Kishan? Okay. Yeah, I mean, for learning purpose, we can write programs in assembly language, but you cannot write huge assembly language programs, right? It is very difficult. So it's better if we write them in C. So what enables this? How can we write a C program and this C program is being understood by the hardware that we have designed? The thing that comes in the middle, anyone can respond? After writing your C program, what's the next step that you do? After writing any program for that matter, compile, right? Yeah, so compilation. So when you write a C program, first it will be pass it to compiler. So compiler is another program. Its whole purpose is to convert the C statements that you write into assembly language statements that the instruction set architecture holds, right? For example, you have written a statement C is equal to A plus B. That will be converted into directly this operation. So the compiler built for that hardware knows what registers that hardware has. Okay, it also knows what instructions that hardware can support. Let's say you have a compiler which does not support multiplication, it only supports addition, right? That means the hardware designers, the chip designers did not design a multiplier within the chip. Okay, they just designed an adder, right? So if you want to multiply 2 into 3, so compiler what it does is it knows, it has an idea about the hardware, right? So when it sees a statement 2 into 3, it will convert this 2 into 3 into 2 plus 2 plus 2, because this compiler knows that it doesn't have a multiply instruction, it only has addition instruction. Now it is the compiler's job to convert the C statement that you have written into the relevant assembly language instruction for that process, right? So you should observe one thing here. So All these things are interrelated. At the end of the day, when you're writing a program for a processor, you should have the supporting ecosystem for it. You should have the compiler designed for it, and you should have this instruction set architecture defined for that processor, right? For 8051 microcontroller. So that's the language abstraction, right? So then comes, if you're talking about operating systems. Nowadays, on your x86 processors, the laptop that you're attending this class with, let's say if you're attending it with a laptop, if it has an AMD or Intel processor, its processor is x86 ISA. So the term x86, has anyone heard this term before? x86? Anyone? Yeah. So the x86 terms that you have heard before, that means it is the x86 instruction set architecture. So AMD has built its own processor based on x86 instruction set architecture. Intel will design its own processors based on the same x86 instruction set architecture. So that is the ISA, right? So you might be confused now. Okay, Intel and AMD, they are using the same instruction set. Then what is the difference between these two chips? It's because they have different microarchitectures. So the addition operation which you are seeing here, or the multiplication operation which you are seeing here, so this can be the same. This instruction is same, but the way that multiplication is done might be different between AMD and Intel. I'm just giving an example. So that is the difference between an instruction set architecture and microarchitecture, right? So that's why you have many different kinds of multipliers, right? Can anyone tell me what are the different types of multipliers you have that you know? Or at least say me different types of adders we have.
Carry skip adder, carry save adder.
Yes. So if you take it as an example, right? Simple example. Yeah. Carry look at. Yeah, half adder is just a adder. Yeah. So if you take an adder as an example, let's say AMD might be using carry skip adder, or Intel might be using carry look ahead adder. We don't know. I'm just taking an example. So their micro architecture is different. Got it? So I just wanted to talk about what an instruction set architecture means. Now, so your x86 processors, they're actually running operating systems as a whole. So now comes a different abstraction level. Now, let's say you have built an embedded system for traffic light controller. So once you have built it, it can only perform traffic light controlling. It can't run any application, right? So using your laptop, you're able to run many different kinds of applications. Let's say Microsoft Word, Adobe Acrobat, right? PowerPoint. All these are different applications. You have a single operating system sitting beneath these. It's able to run different application, user application, and it is able to use the hardware below, and it is running these applications. So that's why operating system pitched in. You want to run any kind of application on any hardware. In the middle, you have an operating system. So this operating system, using what are called as system calls, they transfer the request made by user application to the hardware, right? So best examples are Windows, Unix, Linux, Mac OS, right? That's the thing. Now, so if you want to master embedded systems, you need to have a good understanding of digital circuits, right? Because embedded system is not just about any stage of this. It is about bringing all of these stages together and writing your code for that hardware, for that system that you're designing. Got it? So if you are attending interviews for your embedded systems role by any chance, you should have good understanding of combinational logic, sequential logic. You will anyway have that because you are preparing for VLSI jobs. And above that, you should also have good knowledge on computer architecture, right? So if you want to implement any part of the code efficiently, sometimes during your programs, you may write some of your programs only using assembly for that hardware, such that it can efficiently process your program, right? There might be need here and there to write your program just to diverge from C for some part and write in assembly and get back to C, so that you can run that part efficiently, right? You don't want your compiler to convert your program and make it worse. Sometimes you only want your set of assembly language instructions to run on the processor. In that case, you should also know what are the instructions available for that processor. Here, ripple carry adder is one other adder, basic adder. So you need to master computer architecture as well, right? See, the digital circuits and computer architecture which you need to master. I'll come to RTOS after some time. So the digital circuits and computer architecture which you are mastering for which you need to master for embedded systems, those are also most important aspects that you need to master for your VLSI role as well. If you are applying for any digital circuit design role, they will also ask you all the computer architecture related concepts, right? So those two are common between VLSI jobs and embedded systems jobs. Okay, so we have gone through this arrow which is coming towards embedded systems. And we have also discussed the other few of the arrows. Now let's understand the application. Okay, so remember, for anything that you're trying to solve in your life, especially as engineers, so it's not how efficiently you are able to solve it. The thing that keeps you driving is the motive, why you are trying to solve a given problem, the motive, right? This does not apply to technology only. This applies to any life aspect that you think about. When you're trying to set out on a journey, you need to understand the purpose that you are trying to solve, the problem that you are trying to solve, why you are trying that, why you are solving that problem. Only then you will feel motivated all your way, right, in solving that problem. So that's why we'll talk about some applications of embedded systems, why we need embedded systems, right? And where do you see embedded systems in your daily life? I mean, there are lot many aspects where you see this. Okay, so in automation industry, right, these are all indicated here. If you talk about home, right, home is a best example, especially a smart home. So within a smart home, so you have many things. So basic thing that you find these days in a smart home is a thermostat. So can anyone tell me what a thermostat does? Temperature measurement, right? And based on temperature measurement, what you can control? Basic thing that you can control by measuring temperature of the room. What is it? An air conditioner, right? Smart air conditioner. So all yeah, AC. So AC inbuilt, it has a thermostat. So TV, smart TV, right? Ovens, dishwashers, right? Fire security systems, personal. You have smart cameras as well, right? All these things. Even if you talk about aerospace, right? Air traffic controlling systems. So all of those uses navigation systems, automatic landing, right? Altitude control, engine control. So this is huge space. So there are there are teams which are dedicated to design embedded systems. These embedded chips go into cars, right? So fuel injection system. Let's say there is this concept called as hill descent control. So whenever your car is on a hill, either uphill or downhill, you want to control the car, otherwise it may slip away. So that is also done as an embedded system as a whole, hill descent control. So there are many other aspects. These are some of the things that I've mentioned, that are mentioned here on this thing, right? So there are a lot many use cases around you these days, especially in 21st century, which are built on embedded systems. So what you need to master in order to master embedded systems. So first thing we have discussed is microprocessors. What kind of microprocessors? So it can be a huge microprocessor that you use in an embedded system, right? A simple thermostat need not use the laptop processor, right? So embedded systems are very simple. They have a specific task to do at their hand. So you need to master a 32-bit processor. Mostly that is sufficient. If you have a 64-bit processor, right? I'm coming to that. So I'm explaining the same thing, Srija. So you need to master first a 32-bit processor. The best 32-bit processor that you can master is ARM, either ARM M or A. In coming classes, we will discuss about ARM microcontrollers, especially one microcontroller called as ARM Cortex M, right? So it's better if you master ARM microcontroller or master a RISC-V, right? RISC-V processor. So right now I'm using microprocessor and microcontroller interchangeably, but both are different. Okay, we'll come to that. Now that's the first thing, you need to master it. In order to master a microcontroller, there is certain method in which you should study about a microcontroller, right? That also we'll discuss in the coming classes. And then once you master, I mean, mastering a microcontroller means mastering its instruction set architecture and the set of registers that it has. Okay, that's the thing. So in 8051 also, when you're studying 8051, you study different types of instructions for it, right? In a similar fashion. Yeah, protocols, will come to that. So that is the first thing. Second thing is you need to master programming languages, mostly C, right? So C and assembly. So whenever you want to efficiently run some part of your program, you need to write it in assembly. And mostly this assembly is used in the booting process. For example, so all of you know that C requires C stack to be set up, right? Do you agree with me? In order for a C program to run, you should have stack initialized already. Only then a main function in a C program can run. But when a chip is booting up, we don't have stack initialized, right? That means right from the booting of a processor, we cannot use C. You can only pass instructions to the processor in its own language. That is the assembly language, right? So that's a processor specific. Booting up process is a processor specific. So before stack is even being initialized, you may need assembly, right? So that's the thing. Second thing is mostly C for writing all the other part of your embedded system. So it is the most popular language of choice from firmware development. So nowadays, and I mean, C is most popular. Nowadays, Rust, language called as Rust, is picking up pace due to its edge over C in security aspect. But still, you know, in the industry, all the companies have huge code bases of C. They cannot overnight translate all these C code bases into Rust. That is a significant development time. So that's why C is relevant at least for 10 years from now, right? So C++ is also gaining traction. So, I mean, all of you, I guess, know about C. You might not have studied about C++, all of you. So it's optional. Next is Python. So, I mean, everywhere you go, even in VLSI. So remember, I mean, nowadays, if you want any job, they would simply ask you also to have Python skill as well, even in your VLSI design job. So I was interning at IBM, right? At IBM, I was doing my internship in static timing analysis. There, I had to write a Python script. So all my project was a Python script to split the slack between different critical paths, right? So at the end of the day, Python is the thing that helped me in my internship, right? It's not just about internship. In your daily job as well, you might need to automate many things. So Python is a great, Python gives you that flexibility to automate things in your job. Process automation, right? And one other thing I wanted to tell you is, so you already seen this large language models like ChatGPT writing autonomous code. If you ask it to design, although it is not very great at designing chips now, it might get better. But it can design simple circuits. Let's say if you want to design a traffic light controller, you can ask ChatGPT to give you a state machine. It will give you, right? Maybe accuracy can be 90%, but still 90% is huge, right? So in future, maybe we may have these LLMs doing our jobs. I mean, it can happen, right? We need to prepare for the worst case. So the thing is, in order to be relevant in the job industry, even in the future, in the world of large language models like ChatGPT, you should not stop at mastering your core skill. Let's say your digital design using Verilog or system Verilog. You also master all other aspects of a job. Let's say you want to test your design. So you use some verification language, right? Now you should also understand C, because you also need to validate the entire system, run some firmware on top of it and validate it, right? Similarly for embedded system guys, it's not just about writing embedded software. You also need to master some ways in which we can test automatically. So that is why we have this continuous integration and continuous deployment. Whenever we make change to any embedded program, what we do is we trigger this pipeline. So there is a pipeline which runs automated test cases on top of our change to software. Similarly, it can run some test cases on top of your changed hardware part as well, right? So all of this, you can actually do it using Python, using a software called as GitLab. So what I'm trying to tell you is, so for the future engineer, they should know all the aspects of the job, not just a core skill, not just designing, but also automating the testing as well, right? So just I wanted to say that. Now, so these are the two core skills that you require for embedded systems: microprocessor and a programming language like C and assembly. And then comes the operating systems. So you may need to run your you may need to design your system using a OS called as RTOS, real-time operating system. So it is called as real-time for a purpose. Okay. So generally on our laptop PCs, we have a separate OS called as Windows, right? So it's a operating system designed to run on complex process for complex applications, right? But RTOS is not that. RTOS is designed as an operating system for embedded systems for simple tasks. Its basic purpose is to switch between tasks. Let's say you have an embedded system wherein you are sensing some data. Let's say you are sensing temperature and you want to push this temperature to cloud, right? Wirelessly, right? All our sensors nowadays, they are not wired, right? They only use wireless protocols to transfer data to the cloud, right? Let's say this wants to connect to AWS or Azure cloud, and it wants to send temperature to this Azure cloud, right? And it's also sensing the temperature using the sensor. Now what we have to do here is, there are two tasks. One task is sensing a temperature, and the second task is sending this temperature data to the cloud. So what RTOS does is, it basically manages to do these two tasks at the same time. That means there are slots within the processor. So for in slot 1, you sense temperature. Next slot, you send this temperature to the cloud. Again in the next slot, you sense temperature. Again in the next slot, you send this temperature to the cloud. That means there is one task running. There are two tasks running on the same processor, but a processor can only execute only one instruction at a time, right? A single processor core. How are you doing it? How are you switching between these two tasks? You need an RTOS for it. And RTOS has a mechanism to switch between tasks. Generally, what an operating system also does. You are running multiple applications on your PCs, right? Let's say Microsoft Word, my Zoom meeting, all of these are different applications. But a single processor core is running all these different applications because my Windows operating system is switching between these tasks rapidly. The same thing you may also need in an embedded system. There you have basic operating systems called as RTOS. Best example of an RTOS that you can learn easily from the internet is FreeRTOS, right? And also it is most widely used in industry also, FreeRTOS. Got it? It is basically to switch between tasks, right? So you need to master RTOS concepts as well. And then tools. So whenever you are trying to write a program for a processor, you also need to understand what is the tool chain used for it. The tool chain is, this is the entire set of tools that sit between your C program and the hardware, which we have discussed a few minutes back, right? So you write your C program. First, the C program would be compiled. It would be first converted from C statements. Yeah, JTAG is a debug tool. Yeah, we'll come to it. Yeah, so once you have written your C program, your C programs will first get converted into assembly language statements. Now processor, it cannot understand assembly language also, right? Assembly language is just words, add, mul, right? This is not the language of a processor. Can anyone tell me what is the language of a processor, of any processor in common? Binary, right? Vishesh, you're on point, right? Any processor is a digital circuit at the end of the day. Your digital logic can only understand 0 or 1. That means whatever your compiler, whatever it has converted your C program into assembly statements, at the end of the day, again, this assembly statements should be again converted into binary, right? So add has a binary encoding, mul has a different binary encoding, right? So this this conversion is done by another program called as assembler, right? You have first compiler and then assembler. So that is actually the tool chain, the entire tool chain that is present between your C program and the hardware that you are running. And for the processor that you are using, you need to know its own tool chain. Every processor has its own tool chain, right? So let's say I have add, I don't have mul. My processor doesn't have mul, right? Your compiler should convert any multiplication C statement in terms of addition. But let's say another processor, it will have mul in the instruction set. So compiler can directly use the mul instruction instead of repeatedly adding it, right? So if you are working with some processor, you also need to understand the tool chain that is built for that processor. That is called as generally tool chain, right? So yeah. So Sairam, yeah, I'll tell about that aspect which you're talking about, right? We can get output in fixed time. Yeah. So let me just finish this tool chain aspect, right? So what is the tool chain that you have used? Have you all learned C in your first semester, first year? Yes, right? You have run C in your first semester. Yeah. So in your C programming, did you have lab, C lab? Where, no? Okay. Anyone? Did you have lab? Or you compiled C programs? You compiled C programs, right? Using what tool chain? Using what? I mean, what compiler have you used? Okay, one says GDB, okay, GCC, right? So one says MinGW, one says GCC, right? So GCC is the tool chain meant to run C programs on your x86 PCs, right? So what you have done is basically you have written a C program and you want to run the same C program on the same processor that you have written on. So you have written it on an x86 PC, right? On your laptop or desktop. And also you are running the same program on the same PC. That means you need to have a tool chain which converts your C program statements into x86 statements, into x86 instructions. So that is done by GCC toolchain. Similarly, if you want to run your C program and an ARM processor or on 8051 processor, 8051 is also x86 by the way. So we'll take ARM. So if you want to run your C program on ARM, ARM has designed their own set of tools such that your program will be converted into ARM instructions, right? So for any processor that you take, you also need to understand about its own tool chain. Now comes about debug tools. So debug tools in the sense, how do you debug your program? You have known about breakpoints as well, right? So where you breakpoint, has anyone heard it? Has anyone done it? Breakpoint? Yeah. So the concept of a breakpoint is, so you assign a point at any C statement in your program, and you want to stop your program at that statement. So whenever you have began running that C program, you want your program to stop there at that statement, right? Instead of it running to completion, you want to stop your program at that stage and see what's happening, right? In switch case, let's say in switch case, you have a condition. Based on the condition, you go to a specific case. Now you can put a breakpoint at the switch case and see what that condition is. Is it condition 1? Is it condition 2? Or something like that, right? Based on that condition, the next flow of the program is it should go to the specific case based on that condition, right? So in order to debug all these aspects, you may need debug tools. The best debug tool is JTAG, right? So that's why someone was telling JTAG. So the thing that debug tool brings in here is, so whenever you stop the program at a certain statement, if you have a debug tool, you can actually look at all the registers values at that point. Let's say you have two statements, C is equal to A plus B, and second statement is C is equal to A into B. These two statements are present within your program. Now you can put a breakpoint at C is equal to A into B, the second statement, and you can see what are all the register values within your processor. You can see what are all the memory values within your processor. By looking at this, you can know what's happening within the processor. Is processor correctly executing my instructions, or is it stuck somewhere in any loop or something? All that you can know by looking at all these register views, this memory views, right? All those things. And this Linux command line is common even for any VLSI job that you are attending, that you are doing. You need to, all your tools, all your design tools, mostly they run on a server. That server happens to be a Linux server, right? So you need to master Linux command line in order to do your design also, or write embedded programs also. So that's about tools. And the next aspect is hardware, right? So embedded system, an embedded programmer is not just about writing C programs. It's also about understanding some hardware. So yeah. So you have in Linux, you have something called as user space or kernel space, right? So mostly, right? I mean, for your VLSI job, you only need to know about user space, the command line commands. But if you are working on a Linux system as an embedded programmer, you may also need to know about Linux kernel space as well. So then comes the protocols. So someone was mentioning about protocols. So these are all the protocols, right? Why do we need to know about these protocols as an embedded systems programmer? Can anyone respond? You have PCIe, right? Communication with what?
Software and hardware.
No.
Two software components.
I didn't get you.
Like we are using as an interfaces to communicate between the software components.
To communicate between sensors. That's the answer I was looking for. So all your sensors that you have right now, let's say a thermostat. Thermostats use a temperature sensor. Let's say a common temperature sensor is LM75. So that LM75, it is running at certain clock. Your processor is running at certain clock, right? So when these two devices are running at different clocks, they cannot easily communicate, right? Without you designing some standard such that these two devices can communicate effectively, right? So people have come up with many protocols. These are communication protocols used for communication between your processor or microcontroller and the sensor chips, right? So one is I2C. So I2C is the most famous, and then SPI, then UART, right? UART is a basic one. Yeah, CAN. So yeah, Sriram, can you tell me where CAN is used? Sairam, sorry. Sairam Puvadi, where CAN is used? In automobile, right? So I was talking about engine control, hill descent control, right? All of those things. For all of these control systems that you have in an automobile, you have embedded chips for all of this. So all these embedded chips within a car. I mean, if you just Google it right now, how many chips does a car have, right? How many chips, let's say, does a car like a Honda City has? If you just Google it, you'll get it. It will be easily more than 100 embedded chips within a car. 32 minimum, yeah. So right, so all these embedded chips, they are sensing many things in the car, within the car, and they are actuating things based on the temperature that they receive. They may start to run some coolant system, right? So all of this is happening by communicating between many sensors. So this communication protocols, especially CAN protocol, you use it for automobile embedded systems, right? For generic purpose, for generic sensors, you use SPI, I2C, and UART. So these protocols, their main purpose is to tell about what needs to be taken care whenever you are transmitting data to a different sensor chip from your processor, and what needs to be taken care whenever you are transmitting from your sensor to the processor, right? So they define common set of standard points. If we adhere to that common set of standard points, then we can effectively communicate with other sensors. Okay, so what is a protocol that we use within the processor? Let's say you have processor and you have memory, right? So you want to talk with memory from your processor, from your CPU, you want to talk with memory. No. So I'm asking about within the processor chip. I'm not talking about outside the aspects. I'm talking about what protocol does a processor use these days to talk with memory. within your chip. What are some protocols that you have heard about? Have you heard about AXI, AMBA? Yeah, Vishesh says no, Jaskaran says yes, right? So those are on-chip protocols. Whenever you want to transmit data between different components present on the same chip, you use protocols like AMBA bus, AXI bus, right? But when you want to talk with the chips which are not part of your own chip, you want to transfer data to another chip, right? Then you use these protocols, SPI, I2C, and UART. Yeah, so that's the thing. And then comes what are all the roles present in embedded systems jobs, right? So firmware developer is the first role that we know about. They write firmware code that can run for a specific purpose on your processor. And there are other things. So let's say your board support package. So I mean, if I want to explain about board support package, it is nothing but defining a set of APIs and preprocessor macros. For example, your ARM processor, right? Let's say, or your 8051 processor microcontroller, it has a set of registers, right? So for software programmers to use this set of registers, you need to provide some header file. Within this header file, you define all these registers as just some macros, and also you want to tell the software programmers a set of addresses. That means you are storing your program in set of addresses in the memory, right? You're storing your data in another set of addresses in the memory. So all these memory ranges should also be uh, assigned as a preprocessor macros, and all these macros are placed in some header files, right? So yeah, type def, okay, right? So all these macros related to your processor and APIs related to your processor, you're putting them in separate header files such that any programmer, if they want to work with that processor, they import these header files into their program and use them, right? So that's the basic concept of a board support package, right? There are other aspects as well. See, post silicon validation, because post silicon validation may involve uh, burning your firmware onto the chip and validating few features. Okay. So device drivers, it is mostly related to complex chips. For example, you're making an embedded system which runs a general purpose OS like Linux, right? So you have heard about this term device driver anytime? You have heard about drivers anytime at least? Yeah, Vishesh. So
Yes.
what's the basic purpose of driver? Let's say, I mean, silicon validation real-time example. Yeah, I can tell you a real-time example. So I was at Silicon Labs. So I was actually part of developing embedded applications. There was one of my juniors who was in analog validation role. Yeah, I'll come to that Vishesh again. Yeah, the driver thing. But I'm just explaining some real-time example of silicon validation. So, I mean, I was telling you, right? Silicon validation is also related to embedded role. You also need to flash firmware on a chip and try to test it really if it's working along with the firmware. I'm just taking an example. So one of my juniors was in analog validation team. So he was actually approaching our team and asking us few doubts about the registers that we have corresponding to an ADC. So in the microcontroller which we were designing, right? I mean, which we are writing our software for, there is an ADC within that microcontroller. In order for that ADC, in order to control that ADC, we need to write some registers. Let's say if you want to turn on an ADC, we need to write one to a register. In order to start the conversion, the ADC conversion, we have to enable some bit. right? All these bits are stored in some registers related to that ADC. Now, so to test the ADC, right, to validate the ADC working, these post-silicon validation guys, they had to actually program these registers, right, using code, or manually set those bits in those registers, right? So that's why you also need to have a knowledge on programming registers as well when you're validating your design, right? Yeah, Kishan, Wi-Fi driver in Windows is device driver, sir. Yes. So anything that you are attaching externally needs a driver. Okay. So your operating system is only here to run applications, but you want to have additional functionality. Let's say you want to have a functionality of a mouse attached to your PC, right? Your mouse. You need to have certain GUI drivers, GUI drivers, right? Graphical user interface, because mouse works with GUI only, right? Entirely, right? So whenever you attach a mouse for the first time to your PC, it might pop up saying I'm installing some driver related to this mouse. Whenever you are attaching a new keyboard to your PC, it might pop up saying I'm installing keyboard drivers, right? Has anyone seen those drivers come up whenever you are attaching new devices? Yes, right? Yeah. So basically, installing drivers in the sense. So in order to control keyboard or mouse, there are set of programs which are already compiled for x86, right? For your laptop processor. Now you are just importing that set of programs as libraries within your processor, right? Within your OS, such that OS can use that hardware, use mouse, it can use keyboard, it can use Wi-Fi, right? So whenever you attach a Wi-Fi dongle, it needs to have its own driver. This driver should be first installed within your PC, your laptop system. Only then you can operate that dongle, Wi-Fi dongle. So that's a device driver. Similarly, since there for sensors also you have drivers, right? So in order to work with a sensor, first thing that you need as a driver for a sensor is the calibration. So you need to have some calibrated values. You need to first program that sensor using these calibrated values. Only then the sensor can give you correct temperature values, for example, right? All this calibration mechanism is present within the driver for that sensor. So generally in embedded systems, what happens is in simple microcontrollers, we ourselves write driver for that sensor. So that sensor designer, let's say I2C sensor, it was designed by Texas Instruments. Let's say LM75. LM75 is designed by Texas Instruments. Now, what as embedded software guys, what we do is we go through the data sheet of that sensor. We understand how to do calibration for that sensor, how to calibrate that sensor before you can use it. So in order to calibrate that sensor, we should write some values to the registers of that sensor over SPI or I2C, right? On whichever protocol that sensor works with. Let's say LM75, it works with I2C. Over the I2C, we pass some values to some specific registers which are present within that sensor. Once these registers are programmed within that sensor, only then this sensor can give you correct values. That's called as calibration, right? So simple example for calibration is, let's say my room temperature is, let's say it is 35 degrees, my room temperature. But sensor at the boot up, the sensor is giving actual temperature minus 10 degrees. That means 25 degrees. But 25 is not the right value, right? What we will do is we will program a register saying that whatever you are giving me as the output, add 10 to it. That means if you're actually sensing it as 25, yeah, so if you're actually sensing the room temperature as 25, it will add plus 10 to it because we have written that 10 to a register in that sensor. So every time it senses a temperature, it will just add 10. Then it will produce correct output, 35 degrees. Right? So that is called as calibration. So, right. So as you also will learn in your 8051 course, you will also calibrate your real-time clock, RTC, right? So you will learn about that RTC in your 8051. So that's all about the roles, right? Yeah, so someone has asked me a doubt. So Srija is asking, I have a small doubt that embedded software developer role comes under core or software. Yes, Srija, can you just tell me, based on the discussion that we had just now, will it come under software or hardware?
I think it's a hardware project and that we do just programming. Maybe it's software.
Right, but you are not just writing software, right? You're writing your software consciously. And also in some cases, which I've discussed at the end, you're calibrating a sensor. You're writing some code into the registers of that sensor, right? So you're operating with a sensor at the end of the day. Let's say ADC, right? Sometimes you need to convert analog to digital data. In that case, you need to use that ADC. You need to know the working of that ADC. Only then you will be able to program its registers correctly to get the values correctly. Right? Yeah, Srija. So for example, let's say you have a thermal plant and your temperature, just for example, let's say your temperature is only being given by the temperature sensor in analog format, right? So now there is this situation. So the temperature has risen over certain level. Let's say you have programmed a certain threshold as 40 degrees. If the temperature of thermal plant is going above 40 degrees, you need to start coolant, right? You need to start the coolant system, right? Based on the temperature. And your thermal plant should be cold within some aspect, within some duration. Let's say when your thermal plant has reached 40 degrees, it should be cooled down to 35 degrees within certain duration. If you don't meet this deadline, your thermal plant may blast, right? That is the situation. Now what's happening here? So you're getting a temperature from the temperature sensor in analog format only. But in order to start the coolant, you should go through the processor, right? So processor should first take the temperature data, and based on the current temperature data, it should decide whether to start the coolant system or not. Now, for all of this, you have a certain duration within which you have to complete this task. You need to start the coolant system within 5 minutes of you sensing the temperature, or let's say 5 seconds or 5 milliseconds. Those are tight deadlines. So what you should know about here is the ADC is converting the temperature analog data into digital data, right? It also takes some time, right? So based on the deadline you have, you may have to increase the sampling clock frequency of the ADC, right? So in order to understand this, you need to know the concept of sampling within an ADC, right? Have you understood, Srija?
Yes,
That means
sir. I have understood, sir.
it's not just a software role. So you should basically have understanding of all the aspects that you are studying in your BEC degree in order to be a good embedded programmer. Yeah, so Sairam is asking one more question. So Sairam is asking whether we need any use of TCP/IP in embedded systems. Yeah, this is a good. Again, this is one more aspect of it. So generally, let's say, right, you are building a smart home system. Okay, not smart home. Let's say the example which I've taken, right? So let's say you have a smart bulb, right? Nowadays we are having smart bulbs, and we are also having Android apps for the smart bulb to control the smart bulb, right? Basically, we can turn on the smart bulb or increase or decrease the intensity of that smart bulb using your Android app. How is this being achieved? So this smart bulb, it is not just a bulb. It also has a Wi-Fi processor within it. Okay, it is basically connected to the cloud. So the current state of this smart bulb will be indicated to our app via the cloud using Wi-Fi. So you will also connect the smart bulb to Wi-Fi, right? Your Wi-Fi connection by passing the SSID, your Wi-Fi password over that Android app. Once the smart bulb is connected to the cloud, let's say AWS or Azure, whatever is being used at the backend, this smart home intensity or smart bulb intensity or smart bulb state is being communicated to your Android app over the cloud. Now, in order to transmit data over Wi-Fi, you need to understand TCP/IP, right? You need to understand how Wi-Fi works, how networks work, right? So, in one of my projects at one of my previous companies, Silicon Labs, we had an embedded application wherein we sense the temperature, as I was just explaining you. we need to sense a temperature on one task and switch to another task. This another task, its entire job is to connect to the Wi-Fi and to connect to the cloud over a protocol called as MQTT and send this temperature data to the cloud. And again, after doing this, it should switch back to sensor task. It should again send some temperature. Now it should switch to this MQTT task and it should send it over the cloud. Right? So in these use cases, you may need TCP/IP to understand. Yeah, cleared, Sairam? So whenever you're designing an embedded system, which involves a network aspect, which involves internet, then you may need TCP/IP. Yeah, so Vishesh is asking one more question. So how important is RTOS for fresher role? Yeah, so these days I can say, I mean, RTOS is also important for interviews because people's expectations have risen, right? So, you know, you also need to understand basic aspects of RTOS. At least if not RTOS, you may need to understand operating systems concepts in general. Okay. Basically, what I'm trying to tell is the things that you need to know within an RTOS is the task switching, right? In how many ways you can switch between tasks. You will have something called as priority for a task. So whenever a higher priority task is running, you cannot switch it to another task to be a lower priority task. So based on this priority, so there are different mechanisms of switching between the tasks. You need to understand it. There is simple algorithm called as round robin algorithm, wherein each task is assigned some specific time duration. Let's say 1 second. So every task, it will run for 1 second and it will switch to next task. It will run for 1 second, switch to next task, right? It simply goes in circle, right? Round robin. So that's the thing. There are other mechanisms as well based on the priority. So task switching is the first concept that you need to learn. Second thing is you want to communicate some data between the tasks, right? And you want to synchronize these tasks. Let's say these two tasks are using some common variable, some global variable, right? So when one task is using that global variable, other tasks should not use it, right? So how do you synchronize this? Synchronize between tasks. So concept called as semaphores, mutexes, right? Task synchronization, you need to understand. So task switching, task synchronization, these two things, right? Those are the important concepts of RTOS which you need to understand for your entry level interviews. Yeah, mutex and spin lock is also another task synchronization mechanism. Need knowledge of Linux kernel space or Unix Linux user space or both. It depends on the type of role that you're applying for. See, let's say you're applying for a company which designs embedded systems using ARM microcontrollers. So ARM microcontrollers cannot run Linux, right? They run simple RTOS like FreeRTOS. There you need not know about Linux kernel. But there are some companies which are designing embedded systems which run Linux. Then you may need to program Linux kernel, which is being run on that embedded system, right? So it basically depends on the type of company that you're applying for. But for at the end of the day, the common thing is the concepts of operating systems. Okay, mainly task switching and task synchronization. And the other aspect also that you need to learn is memory management, right? How is your memory managed within a processor, within an operating system? So task switching, task synchronization, and memory management. These are the important concepts as far as OS or RTOS is concerned. Any other questions, anyone? So before ending, right, I just wanted to show you this also. So the thing that we were beginning with, right? At the end of the day, how your problem is being solved by electrons. This is the transformation hierarchy. Has anyone seen the slides? These slides, has anyone seen these type of slides? I've also taken these slides from online, from specific website. Did anyone see these slides before? Just respond.
No, sir.
Yeah, okay. So in that case, if you haven't seen, right, I urge you to go to a YouTube channel called as Onur Mutlu, right? Onur Mutlu. He teaches computer architecture courses, right? A very good course, computer architecture. And you know, at least by the end of this session, that computer architecture is important for both VLSI and embedded system job. Just a sec, I'm typing it. Right, even if you're going into a VLSI job for your career, computer architecture is very important skill to master, apart from just designing circuits. Right, so at the end of the day, our computers are orchestrating these electrons based on the program that you write, and whatever is present in between, this is forming a bridge between your problem that you're trying to solve and the electrons that are being orchestrated within your circuit. Right, and all of this we have discussed, right, in the beginning of our session. So you see, there are, I mean, in our world, there are different types of processors, right? So right from the server processor that you have, that is one end of the spectrum, and the other end of the spectrum, you have a simple, USB controller. That's also an embedded system, right? And you see, all of these has different set of cores. So this is in petabytes of storage, but this has only megabytes of storage. The power that a server might consume might be in kilowatts, but you want a USB controller or any embedded system to consume only few watts, right? Because why our embedded system should consume only less power? Why not more power? Anyone? Battery, right? Which is your on point. All the embedded systems, all the simple sensor embedded systems that we have, they run with a battery, and you want that battery to last longer, right? That's why the power consumption of our embedded systems is in terms of microwatts or milliwatts. But whereas we are not concerned about how much a server consumes power, right? Next is the cost. You see the cost is also varying, speeds is also varying, right? You can see the analogy. So this can be a bullet train, but wherein our embedded systems, they work at scale of a bicycle. So that's why whenever you are trying to solve a problem for a specific goal, you need to understand the entire hierarchy, not just design a circuit, not just write a program. How this program is being converted into your circuit, you need to have a specific approach to design that system. So to design a simple temperature monitoring system, you may take a different approach, but to design a server system, entirely a different approach. Right? So that's why you need this, you have this concept called as transformation hierarchy. Yeah, so this is a simple example for a smart thermostat. So here you are discussing about, this is a microcontroller or an SoC built by Texas Instrument. You see at the heart of it, you have a processor called as ARM Cortex M4, right? And it also has a Wi-Fi processor. So the thing that you asked, right, TCP/IP, all the TCP/IP stack runs on the Wi-Fi processor. ARM Cortex M4, its main purpose is to take in data from sensors via I2C and pass the data to the network processor, such that the network processor can upload this data to the cloud. Right? And you see many different types of sensors integrated. And also, if you want to recognize your voice, right, you should have some DSP chip. It should take your analog voice data and convert it using these ADCs, and it should pass this to our SoC using some other protocol called as I2S. Right? All your audio devices, audio sensors, your microphones work with I2S. Right? So this is a thing. So Srija, I guess, you see, developing an embedded system is not just about software. It involves all the domains, all the disciplines. So does anyone has a doubt? So I also want to explain you one other interesting aspect. This will be the last aspect. So you see, whenever you talk about embedded systems, right, they have evolved in certain fashion. So in the beginning of embedded systems, the people only focus about compute. How do you compute a certain task using an embedded system, right? So under compute stage, we had developed a famous processor called as ARM Cortex-M, right? Cortex-M MCU shipments. Once this is done, you wanted to connect. You don't want a simple microcontroller doing writing some program. I mean, processing some programs. You also want to connect your embedded devices to the cloud, right? So that's where Internet of Things has begun, the connect stage. So within this, you have many protocols. So you have Wi-Fi, you have Bluetooth, right? That's the connect part. And you can see various wireless protocols that were devised at this stage, connect stage, right? And then is the security. So basically, there was a news here. So hackers remotely kill a Jeep on the highway. See, all our devices, IoT devices, are connected to the cloud, right? Your smart bulb is connected to the cloud, or let's say your thermostat is connected to the cloud. Now, since it is connected to the cloud, any hacker can actually hack your devices, your hardware devices from the cloud. That's a possibility. So in the secure stage, what people have done is they have embedded security from the processor itself, from the hardware itself, right? So nowadays you will see security process dedicated within your SoC. Then comes the smart aspect of it. A best example that you can take is there was a news wherein Apple Watch, right? So a biker has suddenly fell and he was unconscious. So Apple Watch has actually understood that he has gone through a seizure, he has gone through seizure and it has detected it, and it has actually called 911, right? It is smart. That means it was able to detect a seizure because it was running some AI algorithm, some neural network on top of it. So this is the current trend in embedded systems, making your embedded system more smarter, right? By running AI algorithms on chip itself, right? So there are two advantages of this. So the first advantage is, let's say in general nowadays, right? Without running AI algorithms on chip, what you will do is, let's say you take the example of an Alexa, right? Your Amazon Alexa, you have an Amazon Alexa. So I'll take a pick pen. We'll just go through one interesting scenario here. Yeah. So is my screen visible? Back again?
Yes, sir.
Yeah. So you have an Amazon Alexa, right? And okay. So this is Alexa. Now you provide your voice to it, right? Your voice. Now what's happening here? You have a microphone, right? Mic. It has an ADC inside it. It is converting your analog voice data into digital data. Now it gives this digital data to the main part of this Alexa, to the processor via a protocol called as I2S, right? Now this is done. Now based on your voice, first it should detect your voice, right? Whether it is a correct person talking to me or not. So it runs a voice detection algorithm, right? So there are two paths that this can take. First path is the previous path, legacy path. Second path is the modern approach. So can anyone tell me what would be the first approach and second approach? Just guess it. Okay, let me continue. So you're giving voice and it needs to run a voice detection algorithm, right? So this is let's say this is a very complex voice detection algorithm. Now it can take two parts. Either it can run this voice detection on the device, or it can actually, the first part that it will take is it will encode this voice data and it will send over the wireless, over Wi-Fi to the cloud. Within the cloud, you have a server, a huge processor, which is running voice detection algorithm on top of the data that it receives. Now it will give this analysis back to the Alexa over the cloud, again over the network. And now Alexa, based on the analysis that the server has done, it will go ahead, right? Whether the voice is detected or not. So that's the first path. Second path is, nowadays what people are doing is, they are designing specific accelerators on Alexa itself. This is a digital circuit whose sole purpose is to run voice detection algorithm or some ML algorithm which is detecting your voice, right? That is on chip. This is making Alexa smarter, right? So that's the thing. So there are two advantages to this second approach. First advantage is, you're not sending any data over the network, over the internet. That means, what is the advantage here? Your voice data, you're not revealing. Privacy, right? So your data is private. It is not sent on over the internet. No one, security. Next is speed, right? So in order to get the response, give the response, you should go through this entire server. It should go to server and should come back from the server onto your device again, and only then you can give the response. That means it is slow. If you run this voice detection on the chip itself, it is fast, right? Response would be fast. So that's the second thing. Less latency. And there is another most important advantage as well. The other important advantage is, whenever you are transmitting data, especially wirelessly, any data that you transmit should go through antenna, right? This device has an antenna to transmit it wirelessly. So just before an antenna, we have something called as a power amplifier, right? So whenever you want to transmit some data wirelessly, you should go through this power amplifier and the antenna, and then your data can be sent wirelessly. So on any chip that you take, on any embedded chip that you take, the part that is consuming the highest power within your chip is power amplifier. That means anytime you want to send any data wirelessly, you are going through power amplifier. That means you are consuming the highest power consumption on the chip, right? So to skip this, what you can do, instead of sending this voice data to the cloud, you can run it on chip itself by designing an efficient processor which can run voice detection algorithms, right? So that's the thing. So the current trend in embedded system industry is embedded machine learning, designing and bringing up these embedded machine learning processors on your chip, right? So maybe if you master VLSI design, right, you may be let's say, if you're mastering your design skills, let's say you might be sitting with a team which might be designing an embedded machine learning processor for some embedded chip, right? And it's not just hardware that you design. Even if you are in embedded system role, you might be sitting with a team who might be writing firmware to it for that embedded machine learning processor, right? So I just wanted to discuss the current trend in embedded systems industry, right? That's the embedded machine learning. So we were at this, right? So this is making it smart. This Apple Watch has included a processor or some small circuit within the Apple Watch to detect seizures, right? Here, limited processing means most data sent to cloud for analysis and action. Networks are flooded with garbage data. Now you can actually distribute your processing over cloud and also on device, right? So these are the companies. So, okay. So there are companies, this Edge Impulse, TinyML, even TensorFlow Lite, their whole purpose is to write software which can run efficiently on tiny hardware, okay? And companies like Mythic, they are actually designing analog accelerators, analog circuits, which compute machine learning algorithms, right? That's the thing. So these are some real world products which I wanted to just show you. So these are products of Silicon Labs. So Silicon Labs is one of my previous company. I mean, it's my previous company where I worked. So their end products are these. So Silicon Labs designs wireless microcontrollers. You have an MCU, you also have a network processor, a Wi-Fi processor, right? A smart lock. You can use it to control a smart lock, right? So a company called as Array was actually a customer of Silicon Labs, which was using our 9116 chips that were being designed by Silicon Labs into smart locks. Next is you can have a few companies who are designing smart meters. So smart water meters or smart power meters. Right now, there is a huge project, one big project, wherein Silicon Labs is tied up with Indian government and they are installing smart meters. So the chips, the network chips present within these smart meters are from Silicon Labs. You can just search over the internet, right? So India smart meters and Silicon Labs, and you will get the info. So people are all also using these sensors, this wireless microcontrollers to monitor beehives, so bee colonies. So to get a honey, right, you need to have a honeybee plant or let's say beehive. So you want to control the pollination, right, and the health of these honeybee hive. So you are monitoring it and sending that monitoring data to the cloud using a wireless microcontroller. So you can also monitor your heart health and send that monitoring data to the cloud using a simple handheld device, right? And you can see a microcontroller as small as a size of 1/10 of a capsule. So it will be mounted to your tooth. So this small processor, which is made of biologically friendly material, so it is actually monitoring your saliva. So based on the saliva, it is deciding whether your tooth are whether your mouth is good or not. Just saying. So you have huge fleets of cars. So whenever cars are manufactured, they are monitored before they are sent out. They are monitored. So they are monitored using again GPS chips. So this GPS have an MCU and also a GPS chip, right? So these are all the use cases of IoT, right? So in US or somewhere, whenever you have huge construction sites, right? People use screwdrivers or people use some machines, right? Now there are many thousands of machines within a huge construction site. Now you need to track all these machines. Otherwise, if any machine is lost, it will be very difficult to find a machine within those huge construction sites. What you can do is you can put a small MCU, wireless MCU, to a machine, and you can track it, right, using BLE. So that's one use case. That's how people are using these IoT chipsets, embedded chipsets. I just wanted to show you that. So yeah, so that's it from my side. How did you feel the session is? How was the session? Yeah, Vishesh says good. Yeah, informative. Thanks. Others? Just want to know the feedback. If you have any question, you can ask me. Yeah, thanks, Poonam. So all of you can follow me on LinkedIn as well. So I'm just typing my LinkedIn profile name. And you can reach out to me on WhatsApp as well. Not a problem. So, right. So yeah, in our future classes, we'll also discuss whatever data structures that we need for embedded systems. Okay, Sairab? So Neeraj Kumar Cheriala, you can follow me on LinkedIn. So I have one request to all of you. So just after we end this session, in the group chat, just post that the session, the feedback, your feedback on the session. Okay. If you agree to this, just give me a thumbs up or raise your hand. Just post your feedback on the session. So Kishan says, his embedded development has divine, sir. Any influence of AI on embedded dev? See, to talk about the worst case scenario, AI has influence on everything that an engineer is doing. The design that you are designing using Verilog, even AI can do that as well. Right? That's the worst case scenario. But the reality is AI is not there yet. Okay. And especially for embedded, right? Whenever you are writing something to control something, to achieve your specific set of goals, AI can do that. So you are the master of your system that you are deciding, right? So there are many aspects involved whenever you are writing some program to achieve some specific task using some specific hardware. So that specificity, AI can't include all of that specificity, right, into the problem and solve it for you. So as an embedded dev, you're still safe. Maybe generic software, right? Let's say a web development software wherein you want to implement a template, web template, AI can do that. So Sairam, you're saying about AutoSAR. Yeah, AutoSAR, whenever you're going into automotive embedded systems, AutoSAR is useful. But for the entry level jobs, they might not expect you to master AutoSAR. Okay, you can just know about the basics of AutoSAR, that's it. Okay, then we can call it a day. Please leave out your feedback on the group chat and VLSI for all. Thank you.